Yeah, hello. This is joint work with Andrei Popescu from Sheffield and Dmitriy from Copenhagen. And yeah, similar to Kathy's talk, this is about how to represent syntax with binders in a theorem prover. Now, basically, Isabelle and what. And I'm trying to just how whatever. We have a binder we name X. We have a body that is a recursive occurrence of the rest of the type. And now the new thing is we have an explicit annotation that, well, this thing should be bound in the body. And we also, of course, support normal, freely constructed constructors that, in this case, model application, we have two fields with recursive occurrences of the type. And that's all that is needed from the user to define these types. Yes? I think it should be.
Yeah, it should be.
Yeah, I'm sharing the whole screen. Yeah, but thank you. So, okay, now we have defined this syntax, but what do we actually want from such syntax? So we want to have some notion of alpha equivalence. With the Brown indices, that's just syntactic equality. Our approach uses names. But the idea is exactly the same. So we can, for example, say, well, it would make sense to say, well, if you have lambda xx should be the same as lambda y. And coming back to the talk about Isabelle's automation, this is just directly provable by many of Isabelle's automation tactics. And why is it provable? Because this definition generates some theorems. Let's make it a bit more readable. For freely constructed constructor, we get normal injectivity as one would expect. And for constructors that have a binder, we get a quasi-injectivity that notes about the variables, and they are up to renaming equal. They equal up to renaming. So what else do we want from such a type? We would want to have a notion of free variables in the type. And indeed, that is also automatically generated by this definition. So if I just look at the simplification rules for this function, we see there's a function fvars lc. I can also rename that if I want. So if I just go in here and call this thing fvars, and then this definition will then tell us the simplification rules for fvars. So yeah, the free variables is just a singleton set. And importantly, as one would expect, in the binding case, we subtract the binders from the free variables of the body. We also want to have some notion of induction, and this being using names, we want to have a variable convention built into that induction principles, meaning we want to avoid the bound variables. And again, this just comes for free. So we have a theorem called fresh induct. And this looks like a normal induction theorem. Aside from this, we have some arbitrary set the user can choose. And as long as this is bounded, we can here in the induction step for our lambda, we know that our binder is in this set. So you can choose any bounded set. And in the induction, we will avoid this binder. So during your proofs, you don't need to worry about clashes with bound variables. In fact, this is not even the most general version of this theorem. There's one that allows you to dynamically avoid changing things, but this is easier to see. So what else do we want? We want usually a renaming function, so we can define renames on the thing. And similar to before, this is also defined. So we call this VB subs for variable substitution. Again, you can rename this, and it has the type you would expect. And as you can see, this is also a parallel substitution that works on any small supported function. That just means for finite syntax, you are only allowed to substitute finitely many things at once. But as Catherine has already hinted at, we do support infinite syntax, and then you are allowed to substitute more things. You also usually want substitution on these things. And again, that's something we provide. Again, with the type you would expect. Again, this is a parallel substitution, and gives you simplification rules, and you can use us in definitions. And more general, we all usually want to be able to define arbitrary functions. And in fact, renaming and substitutions are just specific instances of our general binding aware recursor that are instantiated automatically, because these are functions that are very commonly used, so it makes sense to provide them automatically. I will come back to the arbitrary so the arbitrary functions are implemented as an Isabelle local. You instantiate the local, and the local will give you the function that you want. I will show you a picture of that in a moment. Yeah, right. The next thing we want to do is to make our syntax a bit more interesting. So this is all great, but most systems are able to define the simply typed lambda or the untyped lambda calculus. So one thing we might want to do is to use a non-free data type. So these are all this currently is a mostly freely generated type, and we could of course use lists. But if we can, for example, use a finite set, and we could then just say, okay, our lambda just doesn't bind a single variable, but it might bind a finite set of variables. And again, this works the same way as the syntax before. It generates you all the definitions that you saw earlier, and you can use this to reason. But we're not limited to using these things, using finite things. We also, another thing we could import is from the standard library, the stream co-data type. And then say, for example, let's make our application apply a stream of variables. This is something that nominal Isabelle currently does not support for two reasons. First of all, nominal Isabelle does not support nesting recursion through other types. The other reason is that, yes, this is a co-data type. It's infinite, so this type has infinite support. Nominal Isabelle currently only supports finite syntax. And you can freely mix and match whatever you need. So of course, this would also work with just normal lists or any other data type that you can define in Isabelle. And that's what makes this approach very modular. You can split your definitions. You do not need to define everything in the same mutual recursive group. All right, so jumping back, how does it work? I just want to sketch roughly how our approach is constructed. So this is custom syntax that is parsed by our library. It gets then translated to a pre-data type. This is a non-recursive functor that's that just shows the shape of the data type. And you can see we replaced all the variable positions with a new HOL, and we also replaced recursive positions with new HOLs depending on if the recursive occurrence appears under a binder or not. So you see we have used a different HOL for the body of the lambda, and we use a second HOL for the non-binding recursive occurrences. Then from this, we can define a normal Isabelle data type. These are name-carrying data types at that point, so there's no binding going on yet. This step requires a proof that this shape indeed is this kind of functor. This is done by a recursive procedure and is fully automated, but see the paper for details on that. So once we have this recursive data type now, we can define alpha equivalence and then quotient our raw type, that our name-carrying data type, by this notion of alpha equivalence. And then we arrive at the final type that the user interacts with. However, at that point, we still need to define, of course, the induction theorem, such that this quotient looks like a data type. So for the goal of this work is that the user does not need to care how this is implemented internally. It should look like a mostly normal data type. You get all the theorems you expect from such a data type, and the internal construction is more or less hidden. So I told you I will show you this local that is used to generate arbitrary types later. This is it. And this is its most general form. For most functions, you will not need for the full generality, but there's basically 3 parts to this local. The first 3 parts are the parameters. This is some structure that you can define, this P, which contains the dynamically changing variables you want to avoid with the function. So this general recursor automatically renames bound variables out of the way of whatever you want to avoid. So if you have something that changes during your recursive function, then you can put it in these parameters. And there's also, if you just have a static set of variables you want to avoid, there's this avoiding set. So for most functions, this is enough. So you just have some set of variables you want to avoid, and then define the functions on that. And the last part is then the domain of the function you define, the codomain of the function you define, that defines what you actually do. So we have some notion of changing variables in your codomain. You can extract variables. You also have then this usetor action, which then defines what the function does. So this function is then, this is like a fold. So you get the current at whatever level you are, the current type, and you get whatever was constructed before, and then you can define how should that be constructed to the next step. And all of the renamings and the substitutions are just instances using these locales. So this is also what is available to the user. So we verify our system with several case studies, and we have 2 of them in the paper itself. The first one is Mazza's isomorphism. Mazza defines an infinite lambda calculus, similar to the one we defined earlier, where the lambda binds a stream of variables and the application applies a stream of terms. And in fact, the lambda binds a distinct stream of variables. So it's not just the freely created codata type of streams. It is a subtype on that ensures that all of the variables in that stream are distinct. And that still works as a binder in our system. The second case study is, as Catherine already alluded to earlier, is Popelmark. So we have formalized full Popelmark 1 and 2, A and B. And the interesting part here, of course, is 2B, where we have nested, arbitrarily nested case expressions with record patterns, where all of the binders in the record pattern may only appear once. So then you bind all of the variables in those record patterns in the right-hand side of the case expression. And to our knowledge, this is the first solution to the Popelmark 2B challenge that uses names. Yeah, so a short note on the history of this whole development. At Popel 2019, there was a paper by Blanchette et al. That introduced the notion of map-restricted bounded natural functors as a way of encoding bindings as functors. And based on this notion of functors, we then implemented the system and presented a paper at Popel this year. that introduced that took care of inductive definition. So if you use these syntax to define a type, you usually also want to define some inductive relation or predicate on these types. For example, a beta reduction for a untyped lambda calculus, a typing relation for a typed lambda calculus, or whatever. And how to get the nice induction theorem you saw earlier that we get automatically for the types, how to also recover these for inductive predicates was this paper. In this paper, we also introduced a special induction tactic that can automatically take care of avoiding things. So you just say, please avoid these and these variables, these parts in my goal, and then it will instantiate this thresh induction rule you saw earlier with the relevant things, and also prove this boundedness requirement automatically. So from the user perspective, it just gives you extra assumptions in the binding cases without other requirements. And then now this paper is about how to construct the data types that make all of this possible. So if you are interested in trying this out for yourself, what do you have to do? It's rather easy. You just clone our repository from the artifact. This is also updated continuously with new developments. Then you can just make Isabelle aware of this library, similar how you would do this for the AFP. Import the central file from the library, and that's it. This repository also contains detailed case studies. The two case studies I mentioned, but also other case studies. For example, we have the reduction of a pi calculus in there, which is interesting because the reduction of the pi calculus binds over the relation error, and that's interesting to represent in a theorem prover, and some more. And it also contains detailed example proofs for all of the automation that's going on in the background. So if you're interested in how exactly the construction works, there's a detailed example proofs there as well. Thank you, and